Okay, so last time we started separation of variables, and I guess what I want to do this time is summarize what we did last time, because I think it's important that we follow those steps, and then move forward and finish the problem that we started last time. So this was the problem we were working on. It was rectangular computational domain. We had this partial differential equation to solve. This is sometimes called Laplace's equation. And our boundary conditions are shown here. Right, we have a specified temperature on the left side, a different specified temperature on the top, and then the bottom and the right side surfaces were adiabatic, so temperature gradients are 0. Okay, so here were the steps that we went through. I'm just going to summarize them since we went through them in some detail last time. We said that first thing you have to do is check that your problem can be solved using separation of variables. And next time we'll talk about what you can do to fix your problem if it can't be, but this one could be. We had a homogeneous partial differential equation, and then we had homogeneous boundary conditions in one direction, and that direction was x, right? So you can see that right here. Both of these two boundary conditions are homogeneous, which made x our homogeneous direction, right? And then we had non-homogeneous boundary conditions in y, so at y equals 0 and y equals h. This one in particular was non-homogeneous. So y was our non-homogeneous direction. So with that in mind, we did step 2, which is separate the variables. Separate the variables was this idea that we can express the function temperature, which is a function of x and y, as the product of a function only of x, which we called tx, and a function only of y, which we called ty. And with that substitution, we ended up with these two ODEs right here. And we said that the only way this works is if I choose a positive sign for one of them and a negative sign for the other one, right? So we didn't make this choice arbitrarily. It was important that we choose the positive sign for the ODE that corresponded to our homogeneous direction. So x is our homogeneous direction. That means Tx has to have our positive sign. That's going to form our eigenproblem. We'll get from that eigenfunctions and eigenvalues. And we'll see today why that's really important, because those eigenfunctions have characteristics that are going to be critical in terms of us being able to actually solve the problem. So step 3 was solve the eigenproblem. So basically solve this homogeneous, this ODE in the homogeneous direction. That solution will always give you sines and cosines, at least in Cartesian coordinates. It'll give you sines and cosines. And then we have two boundary conditions that we had to satisfy, right? So C1 and C2 are two undetermined constants. These are our two boundary conditions. We got those from these boundary conditions on our original problem. This first boundary condition told us that our eigenfunctions are sines, and this second boundary condition gave us what we call our eigencondition, which is that this must be true right here. And this will always end up giving you repeated eigenvalues, right? So there's going to be not just one solution to this eigencondition, there's going to be an infinite number, and we just number them, and those are our eigenvalues. So this is the outcome of solving the eigenproblem right here. We should have identified eigenfunctions and eigenvalues, right? Okay, once we did that, then we came back and solved the ODE in the non-homogeneous direction, which is this guy right here. Of course, there's one of these for every eigenvalue, so we have to number them, which we did here. The solution to this equation is Cauchy and Cinch. And then the last thing we did is just say, well, we multiply Tx and Ty together to get T, and that's this guy right here, right? So we have an infinite number of these solutions for temperature. all of which satisfy the partial differential equation and both of these two boundary conditions. None of them at this point do the last two things, which is satisfy the non-homogeneous, the boundary conditions in the non-homogeneous direction. Okay, so that's where we left off. There's a couple more steps to do. Hopefully these steps make sense to you. It'll make more sense after you practice a couple times. But the next step is basically assemble all of our solutions. So we have an infinite number of these solutions, right? One for every eigenvalue. We said that every one of these solutions does these top three things, right? So we can sum them all together and get a solution. And because our problem is linear and homogeneous, at least this part of the problem, then the sum will actually also do these three things, right? If you don't believe it, you can prove it to yourself. But if every one of the terms of this sum does these three things, then the sum itself has to do these three things. And so this is our series solution, right? It still doesn't do these last two things, these last two boundary conditions. So the last thing we have to do is choose these constants, C3 and C4, such that these last two things are enforced, right? So that's step 7. Enforce the boundary conditions in the non-homogeneous direction. So that's just substitution, and then let's see what we get to. So let's look at these two boundary conditions in the non-homogeneous direction. It turns out that one of these boundary conditions is actually homogeneous. So that one's actually going to be really easy to solve for. That's going to be easy to deal with. This last one, though, this non-homogeneous boundary condition, is where we're going to have to learn one more sort of concept, and that is that these eigenvalues, these eigenfunctions are orthogonal to one another. So let's take this and do the easy one first. So here's my series solution. I'll plug it into this requirement that the gradient at y equals 0 has to be equal to 0. So that's just substitution. I take the derivative of this here series, so I'm going to do that term by term. So I'm taking the derivative with respect to y. So let's see, I have the sine of lambda ix, that stays the same. And then I have to take the derivative of each of these terms. So the derivative of cosh is sinh, so that's what I have here. And the derivative of sinh is cosh, so that's what I have here. And I'm evaluating it at y equals 0. So the sinh of 0 is 0, the cosh of 0 is 1. So this guy goes away, and I'm left with just this term here, right? So C4i times lambda I times sine of lambda ix has to be equal to 0. And there's an easy way to make that true, and that's just to set all of the C4i's equal to 0. Right, so basically what that does is kill off all these sinh terms, so I'm left only with this cosh term, and that's what I have here, right? And at this point, we started with 4 undetermined constants for every eigenvalue, so we had a C1i, a C2i, a C3i, and a C4i. At this point, we have either absorbed them or gotten rid of them, so all I'm left with now is C3i. So it really, at this point, is not that important that we keep track of the fact that this is the third of the undetermined constants. We can just call this Ci. So that's what I've done here. This is Ci. So it looks like I'm almost done. Right here is my my solution. This solution does almost everything I needed to do. Right? It does this, and this. I just made it do this. The only thing it doesn't do is this last boundary condition. So that's the last step, is let's make this series solution do what we needed to do at y equal h. So that's just a substitution, and that gives me this equation right here, right? The temperature at y equal h is just, let's evaluate this and put in h for y everywhere up here. So that's this right here, and that has to equal th. So at first glance, it seems like this is pretty hopeless, right? Because I have here an infinite number of undetermined constants, but I only have one equation here that I can use to determine those undetermined constants. And one equation in infinite unknowns is not a good combination. So this is actually where we have to take advantage of the fact that our eigenfunctions are orthogonal, right? So we kind of made a big deal about the fact that we had to do this in a certain way, right? We had to identify which direction was our homogeneous direction. We had to make sure then that in the homogeneous direction we had a certain ODE, and the solution to that ODE gave us some eigenfunctions and some eigenvalues. And here's where all that work kind of pays off, because those eigenfunctions have a characteristic of orthogonality that makes it possible for us to actually evaluate each of these constants, right? So let's start with, what is orthogonality? What does that even mean? So orthogonality of the eigenfunctions just means that if I take one of my eigenfunctions, let's call it eigenfunction I, and I multiply it with another one, let's call it eigenfunction j, and I integrate from one homogeneous boundary to the other homogeneous boundary, right? Then what I'm going to get is 0 for every single combination of eigenfunctions that are different. So if I is not equal to j, when I multiply them together and integrate from boundary to boundary, they will always integrate to 0, right? The only time I won't integrate to 0 is if I'm multiplying one eigenfunction by itself, right? So if I is equal to j, then I won't get 0, which is pretty obvious, since then you're just squaring an eigenfunction and it always has to be positive. So let's think about what this means specifically for this problem. So for this problem, our eigenfunctions are these sine functions, where the lambda I is given by this equation here. So what this says is that if I integrate sine of lambda I times x, so that's my ith eigenfunction, multiplied by sine of lambda j times x, so that's my jth eigenfunction, and I integrate it from one homogeneous boundary to the other, so in this case from x equals 0, because that's where one homogeneous boundary is, to x equals w, because that's where the other one is, then I am guaranteed that that integral is going to be equal to 0. So this quantity here over this integral is going to be positive just as much as it's negative, right? Those two areas will cancel out, and I'll get 0, right? And then it obviously won't be 0 if I'm integrating sine squared of lambda ix or something like that. So that's what orthogonality means for this problem here, right? And that's actually really useful, right? So why is it useful? So here's the equation that governs that non-homogeneous boundary condition, right? And it looks like it's, an infinite number of terms on the left side that has to be equal to something on the right side, and that's not easily solvable. But what I can do is multiply both sides by an eigenfunction, and then integrate both sides from x equals 0 to x equals w. And what this orthogonality is going to do then is it's going to make every single term in this integral go away, because they'll all integrate to 0 except for one, right? And then I'll be left with an explicit equation for that constant related to that term, right? So how do I do that? I take this equation here, and I multiply both sides by an eigenfunction. So let's call that eigenfunction the jth eigenfunction. So I'm going to multiply the left side by sine of lambda j times x, and I'll multiply the right side by sine of lambda j times x, right? No problem. Whatever I do the left side, I can do the right side. And then I'm going to integrate both sides from 0 to w, from x equals 0 to x equals w, right? So I'll integrate the left side from x equals 0 to x equals w, and I'll integrate the right side from x equals 0 to x equals w. Again, no problem, right? Whatever I do to one side, I can do to the other side. And the magic of this is that this integral, right, this is an infinite number of integrals, one for every term. All of these integrals go away except for one, right? And if you want to see that more clearly, let's write this out for a specific case, right? So let's multiply by the second eigenfunction, right? So here's my equation, right? Let's do it for a very specific case where I'm multiplying by sine of lambda 2 times x, right? So the first term then here is going to be c1 times cosh of lambda 1 times h, and then I have sine of lambda 1 times x times sine of lambda 2 times x dx. And then the second term is c2 cosh of lambda 2, because this is the one where I is equal to 2, sine of lambda 2 times x times the sine of lambda 2 times x. The third term, I is now equal to 3, C3, cosh of lambda 3 times h, sine of lambda 3 times h times sine of lambda 2 times x, and I could keep going, right? The next one would be the fourth one and the fifth one. And then on the other side, I just have x equals 0 to x equals w, the integral of th sine of lambda 2 times x. And if you look at this big sequence of terms, this guy here has to be equal to 0 by orthogonality. This guy here has to be equal to 0 by orthogonality. Every other term moving ahead has to be equal to 0 by orthogonality. The only term that's not equal to 0 is this term here, where I'm multiplying sine of lambda 2 by sine of lambda 2. Right, so if I get rid of all these terms over here that are equal to 0, here's my equation that I'm left with. And this is really nice because this is an equation in an unknown. Right? This is a single equation that I could solve for C2. Right? And that's basically the idea, right? If I did this for sine of, if I did this again where j is equal to 3, then I would get a single equation for C3. If I did it for j equal 4, I'd get a single equation for C4 and so on. So basically, I'm going to get an equation for whatever constant corresponds to the eigenfunction that I'm multiplying by, right? And you know, this is in the end what I'm going to get then, right? I'll get Ci cosh of lambda I times this integral of the eigenfunction squared is equal to the integral of whatever I had on the right side multiplied by that eigenfunction, and this is an equation. I have to do some integration to actually solve the equation, but it's a single equation for every single constant in my series solution, right? And here's where Maple really helps, right? Because Maple's really good at doing these integrals, and I'll show you how to do that next.